is Kristen Chitwood, and this research focuses on the economic and ecological benefits of green infrastructure. Green infrastructure is an approach to mitigate stormwater runoff in urban areas and incorporate natural resources to infiltrate rainfall that mimics the natural water cycle. Some examples of green infrastructure include bioretention areas, tree planting, green roofs, bioswales, rain gardens, and permeable surfaces. When it rains, these areas infiltrate, evapotranspire, and in a sense, recycle stormwater runoff. Soil and minerals filter and clean the water, also providing nutrients for plants. Currently in the U.S., polluted stormwater is becoming more of an issue as urbanization and population growth create a greater divide between the natural environment and human habitat. Systems that quickly disperse stormwater away from cities, known as gray infrastructure, provide stormwater prevention, management, and treatment that can be very costly for communities and their residents. Modern cities are more prone to flooding and water pollution because of hard surfaces such as roofs, parking lots, highways, and buildings that prevent stormwater from being properly infiltrated as it would into a field or forest. Runoff from these areas flows into storm drains and, if too heavy, into local rivers, lakes, and streams. Harmful materials are picked up by runoff, such as oils from cars, animal waste, trash materials, and bacteria that damage public health. By implementing green infrastructure, communities and property developers can reduce energy costs, diminish the impacts of flooding, improve public and environmental health, and reduce overall infrastructure costs. Flooding is the most costly natural hazard in the U.S. and has increased in terms of cost it imposes on residents, businesses, and local governments. A 2000 study published in the Journal of Climate found that the U.S. annual flood losses increased from $1 billion in the 1940s to $5 billion in the 1990s. In 2001 alone, there was $7.1 billion worth of flood damage nationally, and it is likely that these values underestimate the actual flood damage costs. Since 1978, the National Flood Insurance Program has paid over $2.8 billion in claims related to localized flooding. Flooding in Montana in June of 2011 caused an estimated $8.6 million in damage to public infrastructure across the state and is expected to continue rising. In 1983, a flood in Tucson, Arizona resulted in $105 million in total damage. Rainfall that would naturally soak into fields or forests now flows away from urban areas in excessive amounts. Excessive amounts of stormwater runoff can ultimately lead to erosion of stream banks, flooding, and contribute to sewer overflows where raw materials are discharged into surrounding water bodies. However, when rain or melting snow creates large volumes of runoff, the total volume of stormwater and wastewater sewers exceeds the capacity of the wastewater treatment plant. When this happens, the stormwater is directly dumped into local water bodies. For example, Figure 3 shows a drainage system without rain and with rain. Due to excess levels of gray infrastructure, high levels of runoff are drained directly into nearby water bodies. Combined sewer overflows dump millions of gallons of untreated water into rivers, creeks, and lakes where people may fish, swim, or may be sources of drinking water, leading to higher costs for polluted water illnesses. However, most stormwater is captured and drained into a wastewater treatment system, also known as WWTS, and through a process of water treatment before it is drained into a local water body. Industrial water treatment is a complex system of technology that includes water treatment, process purification and separation, and wastewater treatment. According to the 2008 EPA Clean Watersheds Needs Survey, the total wastewater and stormwater management needs for the nation are at $298.1 billion, which of $106 billion are directly related to stormwater management and combined sewer correction. Typical wastewater treatment systems can hold about 150,000 gallons of water per day, which can cost from $500,000 to $1.5 million. A study that was published in 2018 established that the national cost of getting sick from being in or around polluted water is $2.9 billion. This price covers medical costs and the loss of income associated with estimated rates of 90 million cases of illnesses per year. Illnesses contracted includes gastrointestinal sickness, ear, eye, and skin-related infections, and more severe pathogen-specific illnesses. So, how does green infrastructure help? There are many different types of green infrastructure that can help to improve the overall quality of life for everyone. It can provide less expensive and more cost-effective approaches to managing runoff. Municipalities and developers may benefit from lower capital costs, land acquisition requirements, operational expenses, and other financial burdens when GI is implemented into new construction, redevelopment projects, or programs to reduce combined and sanitary sewer overflows. Stormwater management practices build around natural hydrologic functions, and increased use of vegetation can dramatically reduce energy consumption. Green roofs, canopy cover, and increased urban green spaces have the effect of making individual buildings more efficient by reducing heating and cooling demands. Figure 4 shows a comparison of gray and green infrastructure. The projects below the dotted line have lower green infrastructure than equivalent gray infrastructure costs. Only one project evaluated had higher green than gray costs. Case studies including Portland, Philadelphia, and New York City and other cities around the U.S. have proven that adding GI will not only provide water quality solutions but help to reduce the nation's energy costs by billions of dollars. Portland, Oregon invested $8 million in green infrastructure to save $250 million in gray infrastructure costs. A single GI sewer rehabilitation project saved $63 million, not counting other benefits of green practices. New York City's 2010 GI plan aims to reduce the city's sewer management costs by $2.4 billion over a 20-year period. The plan estimates that every fully vegetated acre of green infrastructure would provide total annual benefits of $8,522 in reduced energy demand, $166 in reduced CO2 emissions, $1,044 in impaired air quality, and $4,725 in increased property value. It also estimates that the city can reduce CSO volumes by 2 billion gallons by 2030 using green practices at a total cost of $1.5 billion less than traditional methods. Philadelphia has been using policies and demonstration projects throughout the city since 2006 to help promote green infrastructure in planning and development, resulting in drastically reduced CSOs, improved compliance with federal water regulations, and savings of about $170 million. Figure 5 displays the result of a case study that was conducted for Lancaster, Pennsylvania, to calculate the water-related benefits of GI. In combined sewer systems like Lancaster's, utilizing GI could reduce both the capital and operational costs of gray infrastructure systems such as storage tanks and pumping stations. These avoided costs would accrue only within the CSS areas. For the 25-year GI scenario that the case study is based on, the avoided capital cost of implementing gray infrastructure is $120 million, and the avoided operational cost is $661,000 per year. Within the CSS area, these avoided costs would be achieved at a total cost for GI of about $94.5 million, or a total marginal cost of approximately $51.6 million. In conclusion, flooding is the main focus when it comes to implementing GI in cities. However, GI can improve economic costs and ecological benefits on many levels, including energy usage and cost, urban heating, water quality, air quality, and public health. Many communities are either unaware of the benefits of GI or believe it is more expensive or difficult than traditional approaches. Several case studies provide proof that GI is in fact the solution to most of these recurring issues. In order to implement systems like GI, voting for politicians and leaders that make the environment a priority is the most important thing that individuals can do. Local governments and municipalities should invest in installation of alike systems to begin saving money for not only themselves but also their residents and businesses in these areas. I use sources such as the EPA, a City Planner's Guide, and the Center for Clean Air Policy to complete this research. Thank you.